Assalamu alaikum dear students. I hope you are all fine by the grace of Almighty Allah. I welcome you all to the 24th lecture of Thermodynamics 2. Lecture 24. The contents of lecture 24 are Entropy Summary. So here in this lecture we will summarize the chapter of entropy, and then we will discuss and solve some numerical problems. These are from your example problem as well as from the exercise of your textbook as well. And then we will discuss some conceptual question and answers as well. So now we will discuss some conceptual question answer as well. Water at 100 degrees centigrade, quality 50% in rigid box is heated up to 110 degrees centigrade. How do the properties pressure, specific volume, so X is quality, U is internal energy, and S is specific entropy change. So here five properties are given, and the working substance is water, and the initial temperature is 100 degrees centigrade, and final temperature is 110 degrees centigrade. So quality or dryness fraction is given as 50%. So we know that the value of quality or dryness fraction at saturated liquid line is 0, whereas the value of quality or dryness fraction is 1 at saturated vapor line. So for 50%, we know that that region lies under the dome and it contains 50% of vapors and 50% of saturated. It is a mixture of liquid and vapor, so it contains both 50%. So here is the PV and TS diagram are represented. So as you can see that the at the process 1, the system or the water vapor are in the dome region at quality 50%. Since the box is rigid, therefore V is constant. So for rigid box, V is constant. So P will increase in two-phase region. P is equal to P saturation at given T. So as you know that the temperature rise, so pressure and temperature both will increase. So X will increase. We get close to saturated vapor state. So in the TS diagram, you are seeing that 1 to 2 diagonal line. So as the temperature increase, we will get closer to the saturated vapor line. In the PV diagram, it is a vertical line because here volume remain constant. But on the TS diagram, as the temperature change, the value of entropy also change. So as the box is heated, so energy will enter into the system and it will increase the entropy as well. So as Q is provided into the system or the system is heated, so thermal energy is absorbed by the system. Therefore, U or internal energy, that is a function of temperature. So as Q is absorbed and no work is done, therefore the value of specific internal energy will also increase. So we will revise all these properties, that pressure will increase, specific volume will remain constant due to rigid box, X, that is quality or dryness fraction, will increase, and the water will move, or the system will move toward the saturated vapor. Specific internal energy will increase because heat is supplied to the system and temperature is increased. So as U is the function of temperature and pressure, so therefore Q is supplied and no work is done, therefore specific internal energy will also increase, and as heat is supplied to the system, therefore the entropy will also increase. So another conceptual question answer. Liquid water 20 degrees centigrade 100 kilopascal is compressed in piston cylinder without any heat transfer to pressure of 200 kilopascal. So we have given the four properties. So this question is somewhat similar to the previous as well. So here we have a water. Initial temperature of water is given as 20 degrees centigrade. Initial pressure is 100 kilopascal and the piston is compressed. So the pressure is increased and volume is decreased. So pressure is increased up to 200 kilopascal. So the final pressure is 200 kilopascal and no heat is entered into the system. So we are asked to suggest the trend of temperature, specific volume, specific internal energy and specific entropy change. Either they are increased, decreased or remain constant. So the relation, so as there is no heat transfer between system and surrounding, therefore this is an adiabatic system, and dq is equal to T ds is equal to 0, and incompressible because water is an incompressible fluid, therefore dv is equal to 0, and dw, so change of work is pdv, that is also equal to 0. So because liquid water is an incompressible fluid, so in the current lecture as well we have found out the relation for incompressible substance. So when we were discussing that topic, we have assumed that dp and dv are both equals to 0. So here we have temperature, specific volume, internal energy and S will all remain same. So for incompressible substance, the temperature, specific volume, internal energy and S will remain same. Only pressure and enthalpy will increase. So the pressure is increased from 100 to 200, and for uh, liquid or incompressible, H is equal to U plus PV. So as pressure will increase, therefore the enthalpy will also increase. Third conceptual question answer. A substance has heat transfer out. Can you say anything about change in S if the process is reversible and if the process is not reversible or irreversible? So for reversible process, ds is equal to dq by t, that will must be less than 0. So dq will be less than 0. For irreversible process, so change of entropy is the system or entropy transfer plus entropy generation. So ds is equal to dq by t plus ds gen. So as dq is less than 0, but ds gen will be greater than 0. So as we have discussed in the previous lecture as well, the change of entropy generation. So entropy is generated due to the irreversibility present in the process. So for reversible process, there will be no generation entropy generated, but for irreversible process, there will be entropy transfer plus entropy generation. So we cannot say ds depend on the magnitude of dq by t versus d. So they both are independent terms. So dq by t represent the entropy transfer due to heat or any thermal energy during the process. So let's suppose if the heat is added to the system, then entropy will increase, and if the heat is rejected out of the system, then entropy will decrease. So the term dq by t represent the entropy transfer, whereas the term ds gen represent the entropy generated due to the irreversibility in the process. So the magnitude, what are the magnitude of both that the terms individual, so we cannot say directly about their magnitude. So but we know that the term dq by t represent the entropy transfer, and the term ds gen represent the entropy generated during the process due to irreversibility. A substance is composed adiabatically, so P and T go up. Does that change S? So a substance is compressed adiabatically, so pressure and temperature goes up. Does that change S? So if the process is reversible, then S is constant, because ds is equal to dq by t. So if the process is reversible, then reversible adiabatic process is isentropic process. Therefore S is constant and ds is equal to 0. And if the process is irreversible, then the relation will be ds is equal to dq by t plus ds generation. So the term dq will be 0 due to adiabatic process, and ds will be equal to ds generation. So the term entropy generation will be present only due to the irreversibility during the process. Therefore the S universe will increase. So a reversible process in piston cylinder is shown. So PV and TS diagram for the reversible process is shown. Indicate the storage change U2 minus U1 and transfer W1 to 2 and Q1 to 2 as positive 0 or negative. So for W1 to 2, that is equal to integration P dV, that is greater than 0, because the pressure is increasing, and Q1 to 2 is equal to integration T ds, that is also greater than 0, because the change of entropy is greater than 0. So U2 minus U1, it will be greater than 0 for general shape of constant U curves. Further out, in the ideal gas region, the constant U curve becomes horizontal because for ideal gas, U is the function of temperature only. Numerical problem. So the statement of numerical problem is 1 kilogram of liquid water is heated from 20 to 90 degrees centigrade. Calculate the entropy change assuming constant specific heat and compare the result with that found when using the steam tables. So we have to calculate the change of entropy and compare it with the entropy that is found in the steam table. So as the working fluid is liquid water, so it is incompressible and has only one specific heat value. Therefore, S2 minus S1 is equal to C natural log T2 over T1. So S2 minus S1, that is change of entropy, is equal to C. The value of C is 4.184 natural log T2 over T1. So here we have given temperature are in degree centigrade, so we have converted them into Kelvin. So T2, that is 90 degrees centigrade, becomes 363.2, and 20 degrees centigrade, that is T1, becomes 293.2. So change of entropy is equal to 0.895 kilojoule per kg Kelvin. So now we will compare the result obtained with the results that are found in the steam table. So in the steam table, the portion of liquid water or saturated liquid, we will find the value of entropy for 90 degrees centigrade and 20 degrees centigrade, that are 1.1925 and 0.02966 respectively. So when we find their difference, that comes out to be 0.8959 kilojoule per kg per Kelvin, and both of the result are very similar up to fourth decimal. So here is a new topic, that is second law efficiencies. So mostly that topic is usually discussed in the chapter of exergy. So here we will discuss this topic. So we will discuss what is meant by second law efficiency and why it is necessary to find second law efficiency. So second law efficiency is a measure of how much of theoretical maximum Carnot efficiency you can achieve, or in other words, a comparison of the system thermal efficiency to the maximum possible efficiency. So you know that the Carnot cycle, we have already discussed the cyclic heat engine. So we have discussed the Carnot cycle. So we know that the Carnot cycle is based on four reversible processes, and the maximum thermal efficiency that can be achieved by any reversible heat engine can never be greater than the Carnot efficiency. So the value of Carnot heat cycle efficiency or thermal efficiency of Carnot heat engine is maximum. So for practical heat engine, the value of efficiency will always be less than the Carnot heat engine efficiency. So second law is a measure how much the efficiency of the heat engine that is proposed or that is in the discussion has the corresponding. We have a comparison between what is the efficiency of that heat engine that is under discussion and comparison with the Carnot heat engine efficiency. So the second law efficiency will always be between the Carnot and first law efficiency. So in time we will discuss what is first law efficiency and what is Carnot efficiency and how we will calculate second law efficiency. So here is a relation to find the second law efficiency. So eta and second 2i capital I or thermal efficiency of second. ठीक है. So to represent or to find how second law efficiency is calculated, so here is the relation. So second law efficiency is equal to actual thermal efficiency divided by maximum thermal efficiency. So actual efficiency is W actual divided by Q in. So here we have a practical heat engine. So in a numerator its actual efficiency is calculated, whereas in the denominator it is multiplied by the efficiency of Carnot heat engine. So because maximum efficiency or thermal efficiency maximum is can only be achieved by Carnot heat engine, so it is a ratio. Second law efficiency is the ratio between the efficiency of actual heat engine divided by maximum thermal efficiency. So actual efficiency is calculated by W actual divided by Qn, and thermal efficiency maximum or Carnot heat engine efficiency is calculated by W max divided by Qn. So Qn will be cancelled out and the term left is second law efficiency is equal to W actual divided by W max. So maximum work is obtained by only reversible heat engine, therefore W max is changed with WREV, that represent work output of a reversible heat engine. So this relation is for work producing device, and on the right hand side we have another second law efficiency relation for work consuming device. So let's suppose if we are discussing about heat engine and we have to find the second law efficiency of any heat engine, then we will use that relation on the left hand side that are in blue color, and on the right hand side the color of the relation or equation are purple. So for work consuming devices like we are discussing about refrigerator, heat pumps, then we will be using the relation that are on the right hand side that are in purple color. So here we have W reversible on the numerator side and W actual in the denominator. So for work producing, W actual is in the numerator and W reversible is in the denominator, whereas for work consuming device W reversible is in the numerator and W actual is in the denominator. So these are opposite. Similarly, if we have coefficient of performance, so we will have coefficient of performance of actual device on the numerator and coefficient of performance of reversible device or Carnot refrigerator we have in the denominator. Coefficient of performance of reversible device in the denominator. So here we have a example problem. So we have in the two different schematic diagrams, we have shown two heat engines. So here on the left hand side it is heat engine A, and on the right hand side we have heat engine B. So first we will discuss how heat engine A is constructed. So the source temperature for heat engine A is 600 Kelvin, and the sink temperature for the heat engine A is 300 Kelvin, and work output of heat engine A is 30 kilojoules. So the heat that is absorbed by heat engine A from source is 100 kilojoules, and heat that is rejected by heat engine A is 70 kilojoules. And for heat engine B, the source temperature is 1000. So for heat engine A it was 600, and for heat engine B the source temperature is 1000 Kelvin. The same amount of heat, 100 kilojoule, is absorbed from source into heat engine B, and 30 kilojoule of work is produced by heat engine B, and 70 kilojoule, that is same amount for B and A, has same amount of heat that is rejected into the sink, that is also at 300 Kelvin. So you can see, compare that only the source temperature of heat engine A is less than heat engine B, whereas all other parameters are same. Look at, you see that QH of 1 is 100 kilojoules, and QHB is also 100 kilojoule, QLA is 70 kilojoule, and QLB is 70 kilojoule, and WA and WB also equal 30 kilojoules for both, and only difference is the source temperature. So now we will know, after solving this example, we will be able to comprehend why the second law efficiency is important. So you should remember that the properties of heat engine A and B are all similar, except that the source temperature of heat engine A is less and heat engine B is greater. So when we are calculating the thermal efficiency of heat engine A in accordance with the first law of thermodynamics, then the efficiency comes out to be 30%. So efficiency is W over Q. So 30 over 100, that is 30%. And on the right hand side, we are calculating the thermal efficiency of heat engine B in accordance with the first law of thermodynamics. So similar, Q thermal efficiency is W by Q, 30 by 100. So thermal efficiency of heat engine B is also 30% for in accordance with the first law of thermodynamics. Note, we cannot check the performance of any engine based only on the first law of thermodynamics. We must check the performance in accordance with the second law of thermodynamics as well. So in the previous slide we have two different heat engines, but they have similar parameters. So QH and QL and W work output for both engine was same, but the source temperature were different. So heat engine A has less source temperature and heat engine B has greater source temperature. But when we have checked the thermal efficiency based on first law of thermodynamics, that is same for both heat engines. Now we will check the thermal efficiency according to the second law of thermodynamics. So what is the procedure? So from second law of thermodynamics, the maximum efficiency. So if we have uh, changed or replaced with the heat engine, A is replaced by a reversible heat engine, then it has the maximum efficiency. So let's suppose heat engine A is a reversible heat engine, then it will have maximum efficiency. So to calculate the efficiency of reversible device, the formula is 1 minus T 2A over T1A or TL over TH. So maximum efficiency for heat engine A is 50%. So when we were calculating the thermal efficiency according to the first law of thermodynamics, it came out to be 30%. But when we are calculating thermal efficiency according to second law of thermodynamics and considering that the heat engine is a reversible heat engine, then the efficiency comes out to be 50%. Now how to calculate second law of efficiency? To calculate second law efficiency, we will be dividing the actual thermal efficiency with the maximum thermal efficiency that can be achieved. So we will divide 30 by 50. So the thermal efficiency comes out to be 60%. So 30% is the thermal efficiency that we have calculated according to first law of thermodynamics, and 50% is the thermal efficiency that we have calculated according to second law of thermodynamics and considering that the heat engine is a reversible heat engine. And then we have taken the ratio of actual efficiency with respect to the maximum thermal efficiency. So second law efficiency for heat engine A is 60%. Now we will be calculating the second law efficiency for heat engine B. So eta max B. So now we are considering that we have replaced the heat engine B with a reversible heat engine. So the relation to find the efficiency for the reversible heat engine is 1 minus TL over TH. So here TH is 1000, and for heat engine E the temperature of source is 600, and in heat engine B the temperature of source is 1000. So maximum reversible thermal efficiency for the reversible engine is 70%. So here that's how we have calculated. So now to calculate the second law efficiency for heat engine B, we have the relation efficiency of B divided by maximum efficiency of B. So 30 is the amount, 30% is the thermal efficiency that we have calculated according to first law of thermodynamics, and 70 is the value of percentage efficiency that we have calculated according to second law of thermodynamics and considering that heat engine B is a reversible heat engine. So to calculate second law efficiency for heat engine B, we will take the ratio of actual efficiency and maximum efficiency. So second law efficiency for heat engine B is 42%. So now you know that second law efficiency tells the difference. So for heat engine A it is 60%, and for heat engine B it is 42%. So second law efficiency is very important because it also incorporates the source and sink temperature as well. So in heat engine A, it is producing the same amount of work, whereas the source temperature is 600 Kelvin, and heat engine B is producing the same amount of work, whereas the source temperature is 1000 Kelvin. That means the heat engine A is more efficient than heat engine B because both are producing same amount of work and the source temperature for heat engine A is 600 and heat engine B is 1000. So we have to supply more energy to maintain the source temperature, and the efficiency for heat engine B is less than the heat engine A. So this is statement of third law of thermodynamics. It states that the entropy of a perfect crystal is zero when the temperature of crystal is equal to absolute zero. So that statement, we have already discussed that statement in the previous slides as well. So at that time I have asked you to search what is meant by a perfect crystal. So here is the one line definition. A perfect crystal, the atoms and molecules of the crystal are arranged in organized way. It is impossible to lower the temperature of any subsystem to absolute zero. Absolute temperature is only theoretically possible, therefore absolute zero entropy is also theoretically possible. So here in the statement is said that at 0 Kelvin temperature, absolute zero temperature, the entropy is zero. As to achieve absolute zero is only theoretically possible, therefore to attain zero entropy is also only theoretically possible. So here is a conceptual question. A reversible process in a piston cylinder is shown. Indicate the storage change U2 minus U1 and transfer of work for 1 to 2 and transfer heat 1 to 2 as positive, 0 or negative. So here is the reversible process piston cylinder is shown. So these are the two PV and TS diagram are shown that represent a piston cylinder process. So you are asked to indicate whether the U2 minus U1 term or work and heat transfer are positive, negative or 0. So as piston cylinder is a closed system, so the relation for work done is integration P dV. So here from 1 to 2, as volume is increasing, so as volume is increasing, so dV is positive, therefore the value of W1 to 2 is also greater than 0. So on the second, to calculate heat transfer, so for Q1 to 2 integration T ds, so as ds it is an isentropic process shown, so value of entropy is constant, therefore ds is 0 and Q1 to 2 is also 0. So to calculate U2 minus U1, we have first law of thermodynamics. So by energy equation, U2 minus U1 is equal to Q1 to 2 minus W1 to 2. So as the first term Q1 to 2 is 0 and W1 to 2 is positive, but when it is multiplied with the minus sign, that means the value of U2 minus U1 is less than 0. So the second conceptual question is, carbon dioxide is compressed to a smaller volume in a polytropic process with N is equal to 1.4. How do the properties internal energy, specific enthalpy, specific entropy, pressure and temperature change? So these are 5 properties. We have been asked to check whether these properties will increase, their value will increase, decrease or remain constant. So for carbon dioxide we have table 1 A.5. So the value of K is mentioned is 1.289. So for polytropic process the value of N is greater than K. So K in book you should remember sometime it will be written gamma or K. So it is the value of adiabatic index. Similarly, for air the value of N is 1.3 and for gamma it is 1.4. But for carbon dioxide the value of N is 1.4 and gamma or kappa, that is adiabatic index, is 1.289. So N is greater than K and the process curve is given in the figure. So we have PV diagram and TS diagram. So we see the value of pressure. So the process is moving from right to left. So here it is represented state 1 and at state 2 the pressure is increasing and volume is decreasing. So we see smaller volume means moving to the left in PV diagram and thus also increase in pressure. So when we are seeing the TS diagram, then the temperature is also increasing and entropy is also increasing. So here we will see that pressure is increasing, volume is decreasing, temperature is increasing, entropy is also increasing, and enthalpy H is equal to U plus PV. So as internal energy is increasing, therefore enthalpy is also increasing. So the question is, when a substance has completed a cycle, specific volume, internal energy, specific enthalpy and specific entropy are unchanged. Did anything happen? Explain. Yes, during various parts of the cycle, work and heat transfer may be transferred. That happens at different pressure, temperature. The net work output equals the net heat transfer in energy conservation. So dependent upon the sign, it is a heat engine or heat pump. So it may be a heat pump or refrigerator. The net effect is thus a conversion of energy from one stage, one storage location to another, and it may also change nature. Some Q or heat transfer was changed to W or work done, or the opposite. So if it is a closed cycle or cyclic process and volume, internal energy, enthalpy and entropy are not changed, then the value of work done must be equal to the amount of heat that is supplied. So here it is written that the heat transfer happened at different temperature and pressure. So net work output is equal to the heat transfer. So some amount of Q, the heat is transferred to the system, and it is equal to the work that is deduced from the system. Let's suppose 15 kilojoule of heat is transferred to the system. So the pressure and temperature are changed, but work is taken out of the system, therefore the other properties are remain constant. Assume a heat engine with a given QH. Can you say anything about QL if the engine is reversible and if it is irreversible? So for a reversible heat engine, because it's cyclic process, Q by T is equal to 0 and QH over TH minus QL over TL. So as TL is lower than TH, then QL must be correspondingly lower than QH to obtain the net zero integral, because dQ by T for the cyclic process, the value of entropy because the entropy is a state function. For the cyclic process, similar to internal energy, the value of entropy will be equal to 0. So as TL is less than TH, therefore QL must be less than QH, because as their ratio, until their ratio is same to, so their net effect is 0, so the ratio of QH over TH must be equal to the ratio of QL over TL. So for an irreversible process, so there must be an entropy generation term, and for the cyclic integral term for dq by t must be less than 0. Therefore QH over TH minus QL over TL. So this means that QL is larger than before given QH and TH, because let's suppose the ratio of QH over TH is 3, and then QL over TL will also be 3 in the for reversible process. But to in the irreversible process, because that the net effect is less than 0, therefore the value of QL must be greater than, or TL must be less than the in accordance or in comparison with the first one. So the same is written, that means QL is larger than before given QH and T's. The irreversible heat engine rejects more energy and thus gives less work out. So irreversible heat engine, it will give less work and consume more energy. So the third conceptual question, why do we write del S or S2 minus S1 whereas we write integration dq by t or S1 to 2 generation? So the short answer is S1 to 2 is a path function and they are state function, therefore we write it in these ways. So you can read the answer as well. The first part of the change in the storage S2 minus S1 of entropy in the mass, and the second part is the transfer or generation during the process from 1 to 2, because that is a heat entropy transfer due to heat, and that is the entropy generation due to irreversibility. The storage term corresponds to the left hand side of the balance equation for entropy. The integration dq by t represent a transfer of entropy across the control volume surface during the process from 1 to 2, and S1 to 2 generation express the total amount of entropy being generated inside the control volume, and both are on the right hand side of the balance equation. So S2 minus S1, usually write this on the left hand side. So these S2 and S1 are the state properties or specific entropy at state 1 and 2, and dq by t is the value of entropy transfer due to heat interaction, and S1 to 2 is the value of entropy that is generated due to the irreversibility within the process. So here is the home assignment that you should all go through example problem of each topic discussed during the lecture. You should write a handwritten summary report must be submitted. So as discussed in the online session as well, for the all the lecture of entropy related, so as this chapter is concluded in this lecture as well, so you will write a single lecture summary report for these topics. So all students are advised to keep hard copies with them, and if the scenario permit or circumstances permit, if the university is open, then we will be taking these hard copies as well. So all students are advised to prepare previous lecture thoroughly, so there may be a viva or oral question answer session, and you may be asked question related to the topic discussed in this lecture. So take care. Allah Hafiz.